We took part in the SPRIN-D Funke fully autonomous flight challenge. In that challenge, we needed to fly a roughly 9-kilometer parcours with a drone without the use of GNSS, completely autonomous. The parcours consists of 30 different waypoint search areas with a size of 50 by 50 meters. Within those areas, numbered yellow boxes are positioned along with a flag. Over the 9-kilometer lasting parcours, the UAVs had to localize, confirm and overfly those points one after another. We need to solve two main problems. Problem number one is flying fully autonomous, which means there are obstacles in front of us. There will be rain, there will be fog, so we need to sustain that, and we need to still navigate, and we need to still fly and fly the whole parcours. The second thing is the navigation. We're not allowed to use GNSS whatsoever. The UBADRON approach is to use two vehicles. We use cooperative navigation. We have a high-flying UAV and a low-flying UAV. The low-flying vehicle has an infrared beacon, and that beacon can be seen from the high-flying vehicle's camera. We have an infrared camera that can see that beacon and track it relative to its body frame, and then also give us information about, together with range information from the range radio, how far it is away and where it is relative to the high flyer's position. Most modern drones rely on a combination of inertial measurement units for position estimation and GPS for periodic corrections to counteract the drift. IMUs are categorized by the drift performance. Consumer-grade IMUs drift significantly within seconds, relying on GPS for corrections. Commercial and industrial-grade IMUs offer better short-term accuracy, while tactical and navigation-grade IMUs have minimal drift, enabling reliable operation without GPS. Without GNSS, no drift correction would mean a fast deviation of the estimated position, shown in red, from the true position, shown in white. UBADRON makes use of tactical-grade IMUs on their vehicles to provide accurate navigation for minutes without relying on observations of the environment, as optical systems might be blended or the vehicle in smoke or fog. Nevertheless, all such dead-reckoning navigation systems need corrections after some time to counteract the drift. That's where UBADRON's map matching system comes into play. We observe the 3D shape of the environment and compare it to a 3D database to estimate and correct for the drift.
For UBADRON, I was in charge of the LiDAR pipeline. We had two very high-resolution LiDARs on our vehicles, and those scanned the environment. And the point clouds themselves being very big, we compressed them in a data structure called Octree. This allows us to do a lookup of our local laser scan of the vehicle, which is compressed in the same way as the global map, in real time on the vehicle.
Octomaps are kind of efficient storage formats for voxels. So 3D blocks, chunks of, for the navigation portion, a meter or half a meter blocks. And for the path planning, we use 8x8x8 meter blocks that we can stay clear of obstacles quite easily. So also on the fly, we can integrate new observations into the likelihood field of these voxels. So if there's maybe a new hurdle, maybe like a container that is being placed at a certain location, we can see that in the LiDAR and we integrate that into the database. So if we see that the likelihood of one voxel is being blocked increases a certain value, we need to replan. And that's basically a strategic replanning. If that's insufficient, or maybe there's some little obstacles falling into these 8x8x8 meter blocks that we typically see as not occupied, what we can do is we use tactical collision avoidance. And here we use a modified version of the dynamic window approach. So we cast certain trajectories, certain guidance commands, and try to look at which of them may be still suitable for not colliding with the environment, but still moving us forward to the next intermediate waypoint that we have.
We ended up settling for the Intel Up Extreme i14 from the current year, which allowed us to offload some of our workload on the GPU, but also provided enough threads to actually do the map computations and the laser scan lookups in parallel.
We have an image pipeline to identify waypoints because this was one of our main tasks. And for this image pipeline, we use a global shutter cam with high resolution, take these images and then use an AI network to find these waypoints.
So for the challenge, we need to have a drone that can carry all the sensors that we need. And there was no such thing on the market that we could buy at that point. So we need to design our own drone. And our technician Bastian did that in a lot of hours and work hours to design the two vehicles based on an hexacopter design. So it can fly either battery electric during testing or during the challenge with a range extender or a generator where we also need to carry fuel. However, with that we can carry two laser scanners, one forward-looking, one downward-looking, in addition to the cameras and this very nice computer that we have on top of the drones. To speed up the development process, we also developed our own simulation tools. So in the Unity engine, we created physical models, we created the environment, we created sensor models for the real sensors that we carry, so we can already work on the algorithms for, number one, the perception, and also on the action side of the whole cycle.
Facing real-world data was a real challenge for me, because I'm a mathematician at heart. And in the beginning, we were working with simulation data. We were working with proof of concepts, with data matching against the same data. And once the real world got involved and we did actual flight tests and recorded huge amounts of data, we noticed that environment changes. Buildings appear or disappear, trees appear or disappear. So this had a huge role it played a huge role in the accuracy of what we did. So then this parameter came in for another way we have to look at it and have to optimize it.
During the whole preparation for the challenge, we went out a lot to Schönwalde, and the first test which we did there was basically testing the platform and also doing raw data collection, because we programmed the algorithm to get the data, and then we needed for all other algorithms, for example for the map match, for doing other solutions, we needed raw sensor data. So these were the first tests where we just collected the data from the LiDAR, from the IMU, and also for the camera. And these were the integration tests, were of course the most challenging tests, because everything had to work together and all these single interfaces needed to connect. And yeah, of course we also figured out some things which we had to modify again, but it was the last step to our whole challenge. And in the end we had like a good system running with nearly everything we wanted to go to Erde.
So during the final race, we were pretty confident that we can make the whole race, make it to the destination. However, after taking off, we jumped into the cars to follow the drone, and after 58 seconds of flight, one single point of failure, if not saying the only single point of failure, is a power connector from the generator where the batteries are in parallel to the generator going into the electronic speed controllers. There's a connector, and that became loose. So we had a complete power loss after 58 seconds at 20 meters height, and we crashed to the ground.
Yeah, I think in the end it was really beneficial. Even so, yeah, of course we were lucky to win this challenge, but I think for us and ourselves and the whole department, we not only have the sensors now and everything we can work on, but we also have like a good software database and also have developed like a nice atmosphere within the team to work on for future projects.
UBADRON was developing cool new algorithms that have not been combined in a way that they did in this project. So we were able to fly fully autonomous. We showed that in various test flights before the final race. We're able to pick up loads. We're able to show that on the ground and also the precision approach during flights before. We're able to navigate without GNSS, with a LiDAR lookup, with a camera-based system, and with the IMU. we're able to show that in flights before. So even though we didn't make it in the final race, we're confident and happy about what we achieved during the whole progress of this challenge.
Also, how the team worked together, how everyone brought their experience and how that intertwined in the end, and how we grew as a team and everyone was ready to suffer for everyone else. That was a really cool experience, which actually led me to basing my PhD on laser scans.
So I need to say thank you to all our team members, to everyone who's cheering during the final race, and especially also thank you to the SPRIN-D to actually do this event. We had a lot of fun, we developed so many cool things, so thank you, and we're looking forward to future aviation with autonomous vehicles.